Swayam Prabha. Digital India. Educated India.
Let us begin. So, welcome to MA 106 Linear Algebra. So, in this lecture, we will do basic things about matrices. We will begin with fixing notation for numbers and vectors. So, these are the notations. Script P will denote set of positive integers, and N will denote set of non-negative integers. Many times we say natural numbers, but it is not clear whether 0 is included in natural numbers. So this is the notation which is popularized by Richard Stanley. He writes P for positive integers, so it begins with 1, and N for non-negative integers, so it includes the integer 0. Z is set of all integers, negative, positive, or 0, and Q is the set of all rational numbers. R will denote set of all real numbers, and C will denote the set of all complex numbers. The n-dimensional Euclidean space, we will denote it by Rn, and Rn consists of vectors with n components. The components are real numbers. Similarly, we can write Cn to denote vectors with complex entries, or Qn to denote vectors with rational entries, and like that. Okay. The 0 vector, boldface 0 will denote the 0 vector, and from the context it will be clear how many components the 0 vector has. We have following standard operations among vectors in Rn. We can add two vectors with components x1 up to xn, y1 up to yn, and alpha will be a real number. So if we are adding real vectors, we can use alpha to denote the scalar, which is a real number. We can add the vectors by adding them component wise, and this is it is consistent with the physical interpretation of vectors. When we add two vectors, or two say displacement vectors, or two force vectors, or two acceleration vectors, we add the components. So that is the sum of vectors. We can scale a vector by a real number alpha, and we will denote this by alpha x. And when we scale a vector, we scale every component. So the components of alpha x are alpha x1, alpha x2, alpha xn. It's a real vector. We are familiar with the dot product in the plane and in the three-dimensional space. We extend the definition of dot product in Rn. So dot product of two vectors in Rn is simply the sum x1 y1 plus xn yn. So we multiply the corresponding components and add them. And we are familiar with this dot product. Using the dot product, you know that you can test whether two vectors in three-dimensional space or two-dimensional space are perpendicular simply by testing whether the dot product is 0. Okay, and using the dot product, we can also measure angle between vectors. So you know the formula for cosine of angle between vectors. Cosine, if theta is the angle between two vectors in the plane, then cosine theta is simply can be found from the dot product. Okay. Now we move on to fix the notation for matrices. So a m by n matrix, where m and n are non-negative integers with real entries. It's a rectangular array of real numbers arranged in m rows and n columns. And we have standard notation for displaying the row vectors and the column vectors, and a general entry. The general entry is denoted by AJK, and AJK represents the entry in jth row and kth column. Okay, and when we write AJK surrounded by square brackets, we mean that the general entry is displayed, which is displayed in the square brackets, is in the jth row and kth column. Yes, this is the notation for general matrix, and you know that the matrices did not exist 150 years ago, but now matrices are everywhere. Modern technology just cannot be done without using matrices. The data is arranged in rectangular arrays of dimension 2 or dimension 3 or higher dimension, and one does all kinds of wonderful things with this data. So matrix has become part of modern technology, and we manipulate matrices just like we manipulate vectors by adding or taking scalar multiples, etc. So matrix in that sense is a generalization of vectors. A vector is can be thought of as a matrix with one row or one column, but a matrix has arbitrary number of rows and arbitrary number of columns. Uh, so the set of, we will be dealing with the set of m by n matrices with real entries, and then we denote it by R with the superscript m cross n. So m cross n represent the size of the matrix, and R denotes that the entries are real numbers. So just think of all the m by n matrices put together, and this set, we will see later on that it becomes a vector space. And we can add matrices, we can multiply a matrix with a scalar, and we can multiply two matrices with some conditions on their rows and columns. So many things which we do with vectors can also be performed on matrices with some restrictions. So if A is a matrix with the general entry AJK and B is a matrix with general entry BJK, and they are both of the same size, this is important. When we are adding matrices, they have to be of exactly same size. So just as when we add vectors, they should have same number of components. So when we are adding matrices, they should have same size, m cross n. Uh, so we first of all we have to define when two matrices are equal. Well, our objects are matrices, and so first we have to understand when two matrices are equal. So two matrices are equal if AJK is BJK for every J and every K. So the entry in jth row and kth column of A is equal to the entry in jth row and kth column of B for every entry. Then and only then we say A is equal to the matrix B. There are special types of matrices we will be dealing with throughout the course. So n by n matrix is called a square matrix. So the number of rows and number of columns is equal. So it looks like a square when we display it. So we say it's a square matrix. And a matrix is called symmetric if AKJ is equal to AJK for all J and K. That means the entry in the jth row and kth column is equal to the entry in the kth row and jth column. So when you look at the entries on the principal diagonal, that is the entries A11, A22, ANN, they are sitting on the principal diagonal. And with respect to the principal diagonal, the matrix is symmetric. So you can reflect, thinking of a mirror placed on the principal diagonal, and when you reflect, then the matrix doesn't change. Okay. In contrast with symmetric matrix, a matrix is called skew symmetric if AJK is minus AKJ. Okay. And a square matrix is called a diagonal matrix if the entries which are away from the principal diagonal are all 0. That means AJK is 0 for all J not equal to K. A diagonal matrix AJK is called a scalar matrix if all diagonal entries of A are equal. So scalar matrix is a special kind of diagonal matrix. Okay. There are some more definitions. Identity matrix is a scalar matrix in which all diagonal elements are equal to 1. So it's a special kind of scalar matrix. All diagonal entries are 1 and the off diagonal entries are 0. The 0 matrix is the matrix with all entries equal to 0. Okay. So the 0 matrix will play the role of the number 0 when we are adding, and identity matrix, we will see it plays the role of number 1 for multiplication of numbers. A matrix is called upper triangular if ajk is 0 for j bigger than k, which means that entries below the principal diagonal are all equal to 0. Okay. So if at all there are non-zero entries, they can be on the principal diagonal or they can be above the principal diagonal. But all the entries below the principal diagonal, they are 0. So this is called upper triangular. And a similar definition for lower triangular. A lower triangular matrix has all the entries above the principal diagonal equal to 0. So we write it as ajk is 0 for j less than k. Okay. So we have identity matrix, zero matrix, upper triangular matrix, lower triangular matrix. And here are some remarks. A matrix is upper triangular as well as lower triangular if and only if A is a diagonal matrix. So upper triangular means that all entries below the principal diagonal are 0, and lower triangular means all entries above the principal diagonal are 0. So if it is both upper triangular and lower triangular, it must be a diagonal matrix. Every diagonal entry of a skew symmetric matrix is 0, because the condition for skew symmetric matrix is that ajk is equal to minus akj for every j and k. So if you put j equal to k, then it says that ajj is minus ajj, and so that means that ajj is 0. So all diagonal entries of a skew symmetric matrix are 0. Okay, here are some examples. You look at this 3 by 3 matrix, 1, 2, 3, 2, 4, 5, and 3, 5, 6. And you can see that this is a symmetric matrix. So in the first row and third column, we see 3, and the same 3 is sitting across the principal diagonal in the third row and first column likewise. So if you reflect along the principal diagonal, which consists of 1, 4, 0, 1, 4, 6, then the matrix doesn't change. So this is a symmetric matrix, and similarly this is a skew symmetric matrix. So the entry in the first row and third column is 3, and it is minus 3 in the first column and third row. Okay. Similarly for others, and you see that the entries in the principal diagonal are all 0. Okay. So we have the symmetric matrix and skew symmetric matrix. This matrix is diagonal because all the entries above the principal diagonal consists of entries 2, 3, 4. All the entries above the principal diagonal and below the principal diagonal, they are all 0. And this matrix where all the diagonal entries are 2 and other entries are 0, that is an example of a scalar matrix. Okay. Then this matrix is upper triangular because all the entries below the principal diagonal, they are 0. So entries which are significant, that means which are non-zero, they lie either on the principal diagonal or above the principal diagonal. So that's an example of a upper triangular matrix. And this is an example of a lower triangular matrix. All the entries above the principal diagonal, they are equal to 0. Okay. Now we introduce the row and column vectors of a matrix. Row vector A of length n is a matrix with only one row consisting of n scalars. So we are now specializing that vectors with which we are familiar, they are special case of a matrix. A matrix with just one row and any number of columns is called a row vector. So if it has n components, we say it's a row vector of length n, and it has n scalars. Okay, and we write it this way: the first entry we will write as a1, kth entry as ak, and last entry as an. So we don't use the double script notation for this unless we really need it. Okay, so row vectors will be denoted by this. We don't write a11, a12, etc. We simply write a1, a2, ak, an. So therefore, it coincides with our notation for usual vectors in n-dimensional space. Okay. Similarly, a column vector of length n is a matrix with only one column and any number of rows. And we will write a column vector in this way. We display the entries as b1, b2, bk, bn. Okay. So row vectors will be always written like this, and column vectors and row vectors are displayed like this. But for many times, because of lack of space, a column vector can be written in terms of row vector by taking its transpose. So we will come to that later. So suppose we have two matrices of same size, okay, m by n matrices. Then the sum is written as A plus B. And just like vectors, we add the corresponding entries. That is the sum. And scalar multiple of a matrix is for alpha as a real number. Then alpha times A is the matrix which is obtained from A by multiplying every entry by alpha. The special case of this is when we take scale a vector. When we scale a vector, every component has to be scaled. So similar definition applies for a scalar multiple of a matrix. So when we scale a matrix A by alpha, we write it as alpha times A, and this is the matrix where every entry of A is multiplied by alpha. Okay, so that is the scalar multiple. So we have these two important operations among matrices. We can add matrices of same size. We can multiply a matrix by any scalar and get a scalar multiple of the matrix. The operations on matrices. So these are inspired by operations among vectors. We can add vectors and we can take scalar multiple of a vector. So we can do the same thing with matrices. So suppose we have three matrices A, B, C of same size, and there are scalars alpha and beta. So I will, when I talk about matrices, I will assume in the background that these are real matrices. When the context is different, I will say these are complex matrices or rational matrices. But when we talk about real matrices, we will use real numbers as scalars. Okay, when I say scalar, it means they are real numbers if we are dealing with real matrices. So A plus B is equal to B plus A. You can easily check that this is true. So addition of matrices is commutative operation. It is an associative operation. You add, may take three matrices, you add A and B, and then add C, that the answer is same as adding A, and then adding to it the sum of B and C. And if you write down the proof of this, you will see that this is really derived from the corresponding statement for real numbers. Addition of real numbers is commutative, addition of real numbers is associative, and these two rules then translate into the corresponding properties of addition of matrices. That addition is commutative and addition is also is associative operation. So if we don't use brackets, it doesn't cause any confusion. So when I say I have finitely many matrices A1, A2, An of the same size, then when I say add the matrices, it is a unique matrix. It is understood what it is because we can rearrange the manner in which we add these matrices, and because of associativity, it doesn't matter how you add them, how you bunch those matrices to add and arrive at the answer. Okay. Uh, Scalar multiple of matrices satisfies this property that it is distributive over addition. Alpha times A plus B is alpha A plus alpha B. Okay. And again, this is very clear from the definitions. We are adding component wise, and we are when we take scalar multiple of a matrix, we are multiplying every entry by the same scalar. So alpha times A plus B is alpha A plus alpha B. Similarly, matrix multiplication and scalars, they satisfy this fourth property that alpha plus beta times A is same as alpha A plus beta A. Okay, and alpha times beta A is same as alpha beta times A, and therefore we can write it as alpha beta A. So take minus 1 times A, that is a scalar multiple of A. We will write this as minus A, so that we don't have to type or write the minus 1 in round brackets. And similarly, A plus minus B, we will write A minus B, and we understand that this is the sum of two matrices, A and minus B. Transpose of a matrix, this is a very important operation. We take M by N matrix, where the general entry is AJK. Its transpose of this N by N matrix is a N by M matrix, and we write it as A transpose as a superscript, and the general entry is AKJ. Okay, so if I have a M by N matrix, there are M rows and N columns, but its transpose will have N rows and M columns, and the first row of A becomes the first column of A transpose. Second row of A becomes the second column of the A transpose. Similarly, first column of A becomes the first row of A transpose, second column of A becomes the second row of the A transpose, and so on. So that's the relation between A and A transpose. Row vectors of A becomes column vectors of A transpose, right? And we can check that double transpose of A is same as A. Transpose of A plus B is A transpose plus B transpose, and alpha A transpose is alpha times A transpose. So this is how transpose operation behaves with respect to scalar multiplication and addition of matrices. So be careful. Double transpose of A, you get back A. It is clear from definition. And now we can rewrite our definition of symmetric matrix in terms of transpose. A matrix is symmetric if and only if A transpose is A. Okay? A matrix is skew symmetric if A transpose is minus A. Transpose of a row vector is a column vector. Transpose of a column vector is a row vector. Okay, so this is how transpose behaves with respect to addition and scalar multiplication of matrices. Now we define linear combinations of row and column vectors. Throughout the semester, we will be dealing with linear combinations to do various things in linear algebra. So let us define what is the meaning of linear combination of row and column vectors. So fix m and n, and take m scalars, alpha 1, alpha 2, alpha m. So these are real numbers, and take vectors in R1 cross n. That means these are row vectors with same number of components. There are n components in every one of these vectors, a1, a2, am. Then we can take their linear combination, alpha 1 a1 plus alpha m am. This is so we are adding vectors component wise, and we are taking scalar multiple of these row vectors component wise and then adding them. So this is a linear combination, and it is again a row vector of the same size. That is, it has n components. So vectors with n components, row vectors with n components, we can first scale them by arbitrary scalars and then add them. Then this is called a linear combination of these vectors. Similarly, if we have b1, b2, bm as column vectors with n components, so all these column vectors should have same number of components, and suppose these are n components and they are all real column vectors, we can take their linear combination, alpha 1 b1, alpha m bm, and from the definition it is clear that this is again a column vector with n components. So this is called a linear combination of these column vectors. Now, we have very, very special column vectors called EK. These are column vectors where only one entry is 1, namely the kth entry is 1, and other entries are 0. So these are column vectors. EK denotes a column vector where only kth entry is 1, other entries are 0. And if we have an arbitrary column vector, so now you see I have changed. I'm not writing column vector as a column, but as a transpose of a row vector. Yeah? So B is a column vector with components b1, b2, bn, but I'm writing as a transpose of a row vector simply to save space. Okay. So if I have this column vector with components b1, b2, bn, you can check very easily that it is a linear combination of these n column vectors e1, e2, en with scalars as the entries of the column vector. So B is equal to B1 E1 plus BK EK plus Bn En. So this is a linear combination. That means if I take vectors in n-dimensional space Rn, then all the vectors in Rn can be generated by addition and scalar multiplication simply by taking linear combination of these E1, E2, En, and therefore these are called basic column vectors in the n-dimensional space. So n-dimensional space Rn is identical with the space of n by 1 matrices, right? So Rn cross 1 is same as Rn, but we will think of elements of Rn as column vectors, and so therefore it says that all column vectors or all vectors in Rn are linear combination of these basic column vectors E1, E2, En. If we have a arbitrary matrix of size m by n with real entries aj k, then aj is called the jth row vector. So the jth row vector has entries as aj1, aj2, ajn, and similarly we have we can display the matrix in terms of the row vectors. Yeah, it's a m by n matrix, so there are m rows, there are m row vectors a1, a2, am. So we can write the matrix by displaying the row vectors. Similarly, I can write the kth column vector is A1k, AMK transpose. So see how I'm writing the column vector as transpose of a row vector. Okay, so this is the kth column vector of A, and there are if I my matrix is m by n, so there are n column vectors, and we can display the matrix in terms of column vectors. First column vector as C1, second column vector as C2, and nth column vector as Cn. So you will see later on that we can use both these notations to display a matrix either row-wise or column-wise. Yeah. Now we go to the next operation among matrices. This is the matrix multiplication. Right now it is not clear how we are coming up with this strange definition of matrix multiplication. Yeah. But later on, when we study linear transformations, you will see that this definition is kind of forced on us. Okay. So before we discuss product of matrices, general matrices, we define product of a row vector which having n components and a column vector which has n components. So take a row vector and column vector with same number of components. We will first multiply them. So display the entries of the row vector as a1 up to an and the column vector as b1 up to bn transpose. Then the product of this row vector and the column vector is simply the dot product of these two vectors a1 b1 plus an bn. Okay. Yeah. So this is how we take dot product of two vectors in Rn, and we think of this row vector and the column vector as elements of Rn, n-dimensional space, and take the dot product. But the dot product is we are writing by putting the row vector first and the column vector next. So that is the product of a row vector and a column vector. The definition demands that the number of components of A and the number of components of B are equal. So both the row vector and the column vector have same number of components, then we will write A times B. Okay. Suppose I have the matrix A, m by n matrix, then there are m rows. I can display the matrix by displaying the row vectors A1, A2, Am. Yeah? And so recalling that B is a column vector, we will define A times B. Okay, so I'm taking the matrix A, which is m by n, and I'm multiplying on the right by a column vector with n components. So number of columns of A is same as number of components of B. Okay, then we can write A times B. So display the row vectors A1, A2, Am. There are m row vectors, and times B. So all these row vectors have n components, and the vector B also has n components. So we can take the product of A1b, A2b, AMb, and A times B is a column vector with m components, and the components are simply A1b, which is the dot product of A1 and B, and AMb, which is dot product of AM and B. So this is how we are going to write the product of a matrix with a column vector. And of course, we are not taking an arbitrary column vector. The condition is that the number of components of B is same as number of columns of A. And the answer is a column vector of the same size. So the matrix A is sort of acting like a function. The input is the column vector B, and the output is a column vector in the same space. So B, as B changing over m-dimensional space, right? M-dimensional space consists of all the column vectors of size m, of length m or m components. A times B is also varying over all the vectors in the same space. So input is B, output is in the m-dimensional space. Okay, B. So the matrix A is acting like a function. So B had n components, so n-dimensional space into an m-dimensional space. So with using the matrix A, we have a function from n-dimensional space to m-dimensional space. The matrix is m by n, but as a function, it is acting on n-dimensional space, and the output are vectors in m-dimensional space. So in the language of calculus, this is a vector field. Yeah, output are vectors. Yeah, input are also vectors. So the matrix A defines a function on the space of n-dimensional vectors, and the output are m-dimensional vectors. Okay. We will see when we study linear transformation that these are the typical examples of linear transformations from n-dimensional space to m-dimensional space. That is, take a matrix, then A times B is equal to B, and many times we will see that a matrix is understood by its action.